Hey guys, we're going to today go over the study guide. This is assuming that you guys have already done it, and we're just going to go over the answers, okay? The answers here. So these are the topics that you need to go over and you need to study. You can check mark them as you're going through. Let's first talk about bonding. So let's talk about metals. Metallic bonds are formed from the sharing of electrons between metal elements. Okay, because remember, they're delocalized electrons. That's what I mean by sharing, is that the electrons, they're not stuck to one nucleus in a metallic substance. They are free to flow across the surface of the metal. Why do metals conduct electricity? They conduct electricity because the delocalized, remember that word? Delocalized valence electrons. That's why they conduct electricity. So they're free flowing across the surface of the metal. Okay, across the surface of the metal. Okay, that's why they conduct electricity. Okay, so list 3 properties of metals. There's, a whole slew of them, but I put just a few of them here. They're lustrous, meaning they're shiny. They're malleable. I feel like I spelled that wrong. I feel like the E should be for the, yeah. Sorry guys, spelling is not my strong suit. Malleable? Is that right? I don't know. Okay, malleable meaning they can be pounded into sheets and, bent. And ductile means that they can be stretched. Ductile means that they can be stretched into wires. Which metals tend to have the highest melting points? The transition metals. Transition metals tend to have the highest melting points, okay? Ionic bonding. Ionic bonds are between a metal and a non-metal. Or, kids always forget this, so we're going to make a note. So write this down. Or a polyatomic ion. Or a polyatomic ion, okay? So if there's a polyatomic ion in there somewhere, it's an ionic compound, okay? Ionic bonds form from the transfer of electrons. Okay, when an atom loses an electron, it becomes a cation, which is a positive ion. When it gains an electron, it becomes an anion, which is a negative ion. Let's list 3 facts. I put that they have high melting points. Ionic compounds have high melting points. And they conduct electricity. They conduct electricity, but only when they are liquid. So I'm going to put in parentheses an L for liquid. It's a little cursive L. Or AQ for aqueous. Okay, they only conduct electricity when they're liquid or aqueous. Okay. Another thing I put is that they form a crystal lattice structure. You might have had another property listed. I just said pick 3 and put them here. Okay. Covalent bonding. Covalent bonding is between a non-metal and another non-metal. Covalent bonds are formed from the sharing of electrons between nonmetals. It's kind of redundant. Sorry about that. Covalent compounds are also sometimes called molecular compounds. A lot of people have questions about that. Molecular compounds are the same as covalent compounds. 3 facts. They have low melting points. Low melting point. They don't conduct electricity. Do not conduct electricity. Okay? And there are 2 types of covalent bonds. You have polar and nonpolar. Okay? So let's practice figuring out, are these ones ionic or are these ones covalent? So this guy here, it has a polyatomic ion in it. NH4 is a polyatomic ion, so it must be ionic. Okay, that one's tricky because there's no metals in here, but there is a polyatomic ion, which makes it ionic. Okay, this one has a metal and a polyatomic ion, so that's also ionic. This one has a nonmetal and a nonmetal. This is covalent. And remember, how do you know if something is a metal or not? You look at the periodic table. You look at the periodic table, and if it is to the left of the zigzag, it's a metal, with the exception of hydrogen. If it's to the right of the zigzag, it's a nonmetal. Okay? That's how you know. Okay, so tin and oxygen. Tin is a metal, so that must be ionic. This one is covalent. This one is covalent. This one is ionic. This one's ionic, and this one's covalent. Okay, so check your answers there. Okay? All right, flip. Okay, I pre-filled some of this in just to save time. It says describe a nonpolar covalent bond. I said the electrons are shared equally if it's nonpolar, meaning the two elements have about, that little squiggly line means about the same electronegativity or the exact same electronegativity. So they are shared equally. Okay, polar bonds are shared unequally. So the more electronegative element will hog the electrons. Okay. In a polar bond, the atom with the largest electronegativity has a partial negative charge, while the atom with the smallest electronegativity will have a partial positive charge. Okay, so for each of these covalent, or for each of these bonds, I want to know, is it non-polar covalent, polar covalent, or ionic? Okay. Now, if we remember, we're assuming that all covalent bonds are polar unless it's something bonded to itself, or carbon bonded to hydrogen. Okay. These are the only situations in which your covalent bond will be non-polar. If it's something bonded to itself or carbon bonded to hydrogen. Every other covalent bond, assume is polar. Okay, and then ionic, remember, is a metal and a non-metal. Okay, so this one here. Is there a metal? There's no metal, so it must be covalent. If it's covalent, we're assuming all of them are polar unless it's one of these situations, which it's not. So this one would be polar covalent. This one, it's two things, they're not metals, two things of the same thing bonded to each other, so that must be non-polar covalent. Okay, C bonded to H, we just said is non-polar covalent. Because the reason why is because the electronegativity of carbon and hydrogen is really similar. So if it's really similar, that means nobody's hogging the electrons, they're sharing them equally. Okay, this one is going to be polar because it's a covalent bond because neither of these are metals. And it's not one of these two situations, so it's going to be polar covalent. Same with this one, polar covalent. This one has a metal in it, so this one's ionic. This one has a metal in it, so it's ionic. This one is polar covalent. Okay, polar covalent. Now this is a metalloid, but remember metalloids, especially silicon is pretty much always going to do covalent bonding, and that example we've seen many times. Okay, so this one's covalent bonding, because it technically doesn't have a metal in it. It does have a metalloid, but it doesn't have a metal in it, and it doesn't fall into one of these, so it must be polar covalent. Okay, this is a metal, so it's ionic. Okay, what are the 7 diatomic elements? They spell out Brinkelhoff, like that. Okay. What does VSCPR stand for? That is valence, shell, electron, pair, repulsion. Sounds very fancy. But basically, what does it mean? So I already wrote this in. I said the electrons in a molecule are repulsed by each other. So they'll form different three-dimensional shapes based on how many electrons they have in order to be as far away from each other as possible. Okay? That's basically VSEPR theory, is all the electrons are trying to get as far away from each other as they possibly can, and because of that, they're going to form different shapes to get all those electrons and bonds away from each other. Okay? So if we have linear, that's going to be 2 bonds, 0 lone pairs. This is just copied directly out of your notes on molecular geometry. Okay. just for you to remember. Flip. Okay, Lewis dot structures. I went ahead and I already did all the math to save time in this video, and I'm going to draw the Lewis dot structures for you. You need to have showed your math, okay? So I'm going to show you here for PF3, let's see, so we're going to have an F, an F here, and you need to fill up the octet of all these guys, and then you're going to end up, to get the 26 electrons, you need to end up having a lone pair on your phosphorus as well. So I have 26 electrons, everything has an octet, so I have 1, 2, 3 bonds and 1 lone pair around my central atom. So remember, you look at the central atom, you count up how many bonds, 3 bonds, you count up how many lone pairs around the central atom, there's 1 lone pair around the central atom, so when I have 3 bonds and 1 lone pair, that's called trigonal pyramidal. So I'm going to write trigonal pyramidal. Okay? Is this polar or nonpolar? Remember, if there's a lone pair on the central atom, it's polar. Okay? Cool. Okay, let's look at this one, CS2. So I'm going to have carbon. I'm just going to tell you guys, this one's going to end up with a double bond. So check yours and see if you got the same thing. That's the only way to use 16 electrons and to give everything an octet. Okay? I have 2 bonds. Remember, when you're counting up bonding pairs and lone pairs, a double bond counts as 1 single bonding pair. So there's 1, 2 bonds, and no lone pairs around my central atom. 2 bonds, 0 lone pairs is linear. And remember, we're looking at the central atom. There's lone pairs around these guys, but we don't care about that. We're only looking at the central atom here. So this one would be bent. Oh, sorry. I'm so sorry. Just testing you. Linear. Linear. Sorry. Okay. Linear molecules, as long as they're symmetrical, are always nonpolar. And that's because the electrons, there's going to be an even number of electrons on both sides of the molecule. Okay? All right. This one has 24 electrons. So I'm going to have nitrogen. You're going to end up having a double bond on one of these. It doesn't matter which one you choose. And that's the only way to use 24 electrons and to give everything an octet. Don't forget, this is a polyatomic ion. Okay, so you should have had 24 electrons. So if it's a polyatomic ion, you ought to put brackets in a charge. So remember, a double bond counts as 1 bonding pair. So I have 1, 2, 3 bonds, no lone pairs around my nitrogen. So that's trigonal planar. And this would also be nonpolar. I got a lot of questions on that. But so this double bond technically rotates between all of these simultaneously. We just have to draw it somewhere. And you guys will learn about that when you learn about resonance structures next year. Okay, but as it rotates, but anyway, so because of that, it is technically still nonpolar because there's no lone pairs on my central atom, and this double bond can technically be on any of these at any given time. So it's still considered symmetrical, okay? So that'd be nonpolar. Okay, this one has 32 electrons. I've got silicon and 4 bromines. Okay, you got to fill up everything's octet. And this one, because it has 4 bonds, no lone pairs, is going to be tetrahedral. Remember, tetra means 4. So 4 bonds is tetrahedral. And tetrahedral molecules, as long as they're symmetrical, are always nonpolar. Okay, because they have no lone pairs on the central atom. Okay, SO3, this one has, it looks like 24 electrons, but sulfur needs an octet. So you have to put a double, you got to put a double bond on one of these. Tricky. It's a little bit different. We haven't seen this one before. So this one is trigonal planar. Because remember, a double bond counts as 1 bonding pair. So that's trigonal planar. So that's 1, 2, 3 bonds, no lone pairs, trigonal planar. Again, also nonpolar. Okay, SO4 with a -2 charge has 32 electrons. So we're going to have our 4 oxygens coming off here, fill up their octets. Okay, Because it has 4 bonds and no lone pairs, that is going to be tetrahedral. Remember, tetra means 4, so 4 bonds means tetrahedral. And no lone pairs around the central atom. It's also symmetrical, so that would be nonpolar. Okay, moving on. This one says, what are intermolecular forces? I said it's the attraction between 2 molecules. Okay, so not the bonds, but the attraction between the molecules themselves. Okay, so what does like dissolves like mean? It means that polar things dissolve polar things, non-polar things dissolve non-polar things. Okay, that's why you can dissolve salt in water because they're both polar, but you can't dissolve oil in water because water's polar and oil's non-polar. So 3 types of intermolecular forces we learned about are London dispersion forces. I'm going to abbreviate. Dipole-dipole interactions, and hydrogen bonding, H bonding. Okay, those are the 3 we learned about this year. Which type is the weakest? London dispersion forces are the weakest. Okay, let's flip. Okay, what type of intermolecular force is the strongest? Hydrogen bonding is the strongest of the 3 that we've learned about this year. Hydrogen bonding only happens with molecules that have hydrogen bonded to fluorine, oxygen, or nitrogen. Okay, so for each molecule, tell what type of intermolecular force is present. So in this one, I've got a hydrogen bonded to a fluorine, so everything is going to have London dispersion forces, just so you know. So everything experiences these guys, because I want to know all the types. Everything experiences London dispersion forces. Okay? This guy is going to be also experiencing dipole-dipole and hydrogen bonding. Why? Well, if I draw its Lewis dot structure, HF, it's just an H with an F, looks like that. Okay, this is clearly not symmetrical, so it's definitely polar, okay, which makes it experience dipole-dipole. It also has hydrogen bonded to fluorine. Whenever you have hydrogen bonded to fluorine, it can do hydrogen bonding with other HF molecules, okay? This guy can also do dipole-dipole and hydrogen bonding. How do I know that? Well, I drew the Lewis dot structure. So Lewis dot structure looks like this. I'm doing it kind of quick, but because it has a lone pair on the central atom, it's going to do dipole-dipole because it's a polar molecule. It's going to do hydrogen bonding because it has hydrogen bonded to nitrogen. Okay, that's how I know. Okay, Br2 is only going to do London dispersion forces, and that's because Br2 it's just a Br attached to another Br. Okay, diatomic elements are non-polar. They're going to share equally. That's all it's going to do is London dispersion forces. CH4 is going to also just do London dispersion forces. That's it. Because CH4, if you draw its Lewis dot structure, it looks like this. There are no lone pairs around the central atom, so it's not polar. So it can't do dipole-dipole, and it does not have hydrogen bonded to fluorine, oxygen, and nitrogen, so it also can't do hydrogen bonding. It can only do London dispersion forces. This guy can do London dispersion forces. It can also do dipole-dipole. Okay, can it do hydrogen bonding? No, because here's the Lewis dot structure. Because there's a lone pair on the central atom, it can do dipole-dipole because it's polar, but it can't do hydrogen bonding because hydrogen must be bonded to fluorine, oxygen, and nitrogen to do hydrogen bonding, and it is bonded to phosphorus, so it can't do that. Okay? All right, let's look at this. Okay, molecules with stronger IMFs have higher boiling points. For each pair, tell which molecule will have the higher boiling point and why you think that. Okay, so out of these 2, this one's going to have the higher boiling point because it can do, has hydrogen bonding. If it can do hydrogen bonding, its intermolecular forces are stronger, so it's going to have a higher boiling point. Out of these 2, okay, neither of them can do hydrogen bonding, neither of them can do dipole-dipole because they're both diatomic elements, so all they can do is London dispersion forces. So how do you know which one has stronger London dispersion forces? Well, whichever one is bigger and has more electrons is going to have more strong London dispersion forces. So because iodine is bigger, it's going to be the winner here. So I'm going to say because it's bigger, it has more electrons. Okay, when you're comparing two that are doing London dispersion forces, you go with the more massive element. Okay, these two. This one can do hydrogen bonding, this one can't. So again, hydrogen bonding wins. Hydrogen bonding for the win. Okay, out of these two, which one? Okay, well, if you were to draw this out, neither of them are polar. Neither of them have hydrogen. So you're, again, just comparing London dispersion forces. Well, which is bigger, F2 or CF4? Well, this has a lot more going on in it. It has a lot more electrons, so this one's going to be the winner. So bigger has more electrons. Has more electrons. Okay, this one says draw two H2O Lewis dot structures, show the dipole moments for each, and their bonding using the arrows, show the partial positive and negative charges. Okay, so let's talk about this. So we're going to have a water molecule like this, and then another water molecule like this. Okay, these are our two water molecules. It says show the dipole moments for each of their bonds using arrows. So if you remember, I don't know why I drew my electrons like that. It should be in a pair. Okay, so if you remember, when you're doing the dipole moment, you just draw an arrow pointing to the more electronegative element, like that. Okay, and you only have to do this if I ask you specifically in a problem to do this. Draw towards the more electronegative element. How do I know oxygen's more electronegative than hydrogen? Because oxygen is closer to fluorine than hydrogen is. Okay? And then you remember you put a little plus sign on this end, like that. Okay, I'm just showing the dipole moment. I'm showing where the electrons are spending most of their time. And I'm just going to highlight it to make it a little bit more obvious. This is where electrons are spending most of their time. They're spending most of their time with oxygen. Okay? And then it says, show the partial positive and negative charges. Okay. And guys, if you look at the back of page 17 in your notes, this is pretty much exactly what I have there. So this would be up here where the electrons are hanging out. That would be a partial negative. I put a little squiggly delta symbol. This one would be partially positive, partially positive, partially negative. And then next to my hydrogen is partially positive, partially positive. Then it says, show where the hydrogen bonding would occur between the two molecules using a dotted line. So this partial positive area is going to be attracted to this partial negative area. So I probably could have drawn this better, but basically these two guys are going to be attracted right there. The hydrogen and the oxygen are be attracted to each other. This is the hydrogen bonding. This is not a hydrogen bond. Remember, hydrogen bonding is not actually bonding. Hydrogen bonding is a misnomer. It means it's the attraction that happens between two molecules, okay? But it just happens to happen where there's hydrogens. So the hydrogen bonding is right here. It's the attraction between these two molecules, between the partial positive end of this one and the partial negative end of this one, okay? Okay, when an element loses an electron, it has a positive charge and its radius gets smaller. This is review. When an element gains an electron, it has a partial negative charge and its radius gets bigger. What is the trend on the periodic table for atomic radius? Atomic radius gets bigger towards big fat francium. Okay? Atomic radius increases as you go down to the left. This one says, how do you know when a chemical name needs a Roman numeral? Which elements do not need a Roman numeral? You know it needs a Roman numeral if it's a transition metal. These guys do not need a Roman numeral. Group 1, Group 2 of the metals, Group 1 and 2 do not need a Roman numeral, and the ones in our triangle do not need the Roman numeral. Okay? And when I say triangle, you guys should all have your triangle marked on your periodic table. If you don't, now is a wonderful time to do that. Let's do it. Your triangle are these guys right here. These guys don't need Roman numerals because these ones are all +3, these ones are +2, this one's +1. Okay? And if you need to drop that in, this guy's +1, these guys are +2, and these guys are +3. You write that in. All of these other ones need Roman numerals, except hydrogen, because hydrogen is not a metal. Okay? All right, cool. Okay, what are these prefixes? This is mono, di, tri, tetra, penta, hexa, hepta, oct, and nona. Okay? Flip. All right, I'm going to show you guys my answers to this. Let me zoom out. I got some questions on this asking basically what does it mean by is it transition metal? Like what about if it's in the triangle like zinc or silver? And the answer is basically I'm just asking right here. I'm asking, does it need a Roman numeral? That's really what I want to know here. Does it need a Roman numeral? Yes or no? Okay. Okay. So if you need to pause that, you can, and check your answers there. That's all I have for you guys. Good luck on your test.